Well, good afternoon, everyone, from Ithaca, New York, home of Cornell University. I'm Nicholas Phillips. We're happy to welcome back Frank Weiss, a professor of engineering here at Cornell and the director of Cornell Center for Materials Research, or CCMR. CCMR is working with FuseHub, New York's statewide manufacturing extension partnership, or MEP, on a new program. This initiative enables New York State manufacturers to access the guidance and support they need to replace materials in their products with more sustainable options. And just as a quick side note, for more information, check out the link in the program overview section on the registration page, and we'll also drop it in the audience chat as well. MEP will provide financial and technical assistance to industry partners who are looking to improve or replace materials in their products. Today, we're going to continue our discussion around the complexities and innovations within the field of advanced materials. Professor Weiss, thank you so much for coming back.
My pleasure, Nick. Happy to be here again.
It is really so great to have you. So last time you were here, we talked about, what advanced materials are. The title of our discussion today is obviously use-inspired design. And so to kind of start our conversation off, I want to dive a little bit deeper on where advanced materials come from. So I'm hoping you can give us a little background. What are the traditional sources of advanced materials?
Well, of course, really traditionally, materials have been the materials that are available in nature. Okay. So people had wood, people had metals, and then over the years, people developed some basic ways to enhance their properties, some chemical ways, some thermal processing for metals, etc. And so this is what we would probably call traditional materials.
Okay.
And of course, those processes have become more and more refined over the years.
Of course. And how do the properties of natural advanced materials compare to those of some of the synthetic ones?
So if you recall from last time, we've gone from using materials in nature and developing processes to enhance them to actually thinking about desired material properties from the beginning.
Okay.
And then people actually use the word materials by design. So now people do this, but it requires a much deeper form of science. People have to understand the atomic and molecular origins of material properties. And this is why development of new synthetic materials typically takes a big team and a lot of iterative science to get it done.
Yeah, I remember last time we were talking a little bit about the process and the multiple members of the team that's required to, develop some of these advanced materials and things
to
like
really
that.
Develop a new material, yes.
Yeah, I do remember.
You asked how do the properties differ or compare, and what I would say is, of course, we started making synthetic materials to make properties that were better than anything available in nature or that didn't exist in natural materials.
Oh, wow. Okay.
But I would say now it's probably more fair to say that the properties aren't necessarily better or worse.
Okay.
They're different. We prioritize different properties now. So as one example that we'll see, we have great engineering of plastics.
Of course.
But now we have a problem with pollution with plastics. So people are looking into ways to make plastics that are just good enough to do the job, may not be as good as prior materials, but good enough and be more friendly to the environment. Just as one example.
Very, very great example, actually. And with that, what does use-inspired design mean for material scientists?
So most scientists think of their job as to generate new knowledge.
Okay.
If the knowledge helps solve a problem, that's wonderful. But if not, that's okay. It'll be there for the future.
Of course.
Sometimes people call this curiosity-inspired research. I'm not sure it's completely fair because it sounds a little flippant or something. Use-inspired design interchanges the role of knowledge in applications.
Okay.
It starts from the application, and knowledge is generated in the course of meeting the need of the application. So this is what happens when you can't just put together known things. And this approach, use-inspired design, is very common among engineers and applied scientists, as opposed to scientists who are trying to understand nature as deeply as possible.
And I'd be interested to know, where are some of these designs being used in the real world?
Oh, well, when we talk about advanced materials, the things that come to mind tend to be things like high-tech industries, microelectronics, energy storage, telecommunications, the internet, et cetera. But advanced materials are all over the place in everyday products, right? It's very easy to take materials for granted. Consumers use products. They don't sit and think about the materials they're made of, right? We'll see a lot of good examples today. Anything that's manufactured depends on materials. In fact, my first boss used to say to me that every engineering problem is ultimately a materials problem. It's a bit of an exaggeration, but I think there's some truth to it. So coming back to your question about examples, CCMR works with all kinds of companies, not just high-tech companies. We're going to show examples that include the most common consumer goods, such as coffee cups and clothing,
Of course.
Apparel designed to protect soldiers and workers in dangerous environments, and even medical instruments to be used in surgery. So it's quite a range, and those are probably not the things people would think of when they think of materials.
Of course. I like what your old boss said. I'm gonna remember that.
You can see I did
in mind,
years later.
Of course. And, for more information on this, let's turn to Juan Hinestroza, professor in the Department of Human Ecology, and Christopher Thomas, who's the founder and CEO of Return Bio.
My name is Juan P. Hinestroza. I'm a Rebecca Q. Morgan Professor of Fiber Science and Apparel Design at Cornell University. My background is in chemical engineering and material sciences, and I work in different types of materials, from natural materials to synthetic ones.
Hello, my name is Chris Thomas. I'm the CEO and co-founder of Return Bioworks. At Return, we're developing sustainable solutions, sustainable materials to replace toxic, outdated plastics in fiber-based food packaging. Right now, there is a global crisis of plastic pollution. It's something that consumers are aware of. It's something that industry is keenly finding to be a problem, and they need to solve this. Their most hoped-for solution to solve this is with a biopolymer. Our technology at Return enables us to upcycle abundant fiber-based waste materials from these same manufacturers into a platform technology of tunable, sustainable, recyclable, and functionalizable biopolymers. The problem is, for us, this works at lab scale, this works in small demonstrations. We need to prepare this for manufacturing, for manufacturability. That's why we came to Juan and the CCMR to figure out how to get these hydrophobic polymers to play well with industry standard latexes and aqueous emulsions.
So we were connected through the Jumpstart project that helps New York State-based small companies to have access to state-of-the-art facilities like the ones we have at Cornell. Now you are trying to replace a synthetic material that is inside the coffee cups with a natural material. And it's very difficult to do that because you are dealing with hot temperature coffee, for example. We are dealing with the pressure that the coffee makes on the walls of the coffee cup. And so this unique challenge was excellent for our students to tackle on and for the facilities that we have here at Cornell.
Right, and that is the major challenge, that we're working with these bio-based materials that honestly will never be quite the same as your original plastics, as PFAS, as polyethylene. Those are over-engineered for these purposes, though. You don't need your Starbucks coffee cup to last 1,000 years. 15 minutes is the average time it takes to receive your coffee, to drink it, and to throw it away. And when you throw it away, it needs to be recyclable or compostable. Right now, the polyethylene that's coated inside there traditionally renders it unable to be going into either of those processes. And so we need to figure out how to take our biodegradable materials, these polyhydroxyalkanoate copolymers, and get them to have the same functionality that you find with this polyethylene.
And it turned out really good because we work on fibers, but these fibers are actually based on organic waste, agricultural waste. We take waste as a raw material for the process. And then we use the capabilities that we have here to do the characterization and to prove to manufacturing companies how we can actually process these materials. So in that sense, the CCMR help us facilitate this translation of a lab project, a small company, to a larger manufacturing scale.
This is important for us because our next major milestone is proving out the manufacturability of this material in these processes. And while I mentioned polyethylene, which is typically extrusion coated, the future of sustainable packaging is in aqueous emulsions. It's in 3D formed molded fiber, which is the quickest growing packaging segment in sustainable packaging. And there, you cannot be extrusion coating. You need something that's going to be ubiquitous, that's going to work for all kinds of materials. And these aqueous emulsions, these early results from Juan's laboratory have been excellent. It's what we're using to interact with our customers in industry and to take it to the next step in scaling up this technology from a lab practice into a sustainable coffee cup in a customer's hands.
So next time you have a coffee in a coffee shop, maybe those coatings will come from our lab and from Return Bio.
Well, thanks, Juan and Chris. So interesting. I was listening to the video and I was thinking, my Starbucks cup and everything. Oftentimes when I go to Starbucks and get the cup, I'm like, wow, this is an advanced material. But with that, I'm wondering how common is the use of some of these advanced materials when it comes to, food packaging?
Well, not just food packaging, but a variety of applications. Of course, sustainability is a priority now in designing new materials and processes. So let me go through a few slides here. Don't worry, not too many.
Okay.
Of course, we're all familiar with the food packaging that we use. May not seem high tech, but it's used millions of times a day in the top row there. We have to be able to package food to last for a long time. And of course, we want strong and inert carriers for our food. Other areas, of course, batteries and energy storage are in the forefront of the news these days. And here I'll just highlight electric cars shown there at the bottom left, a huge and growing segment of the battery and energy storage industry.
Of course.
We all walk around with 1 billion transistors in our pockets now and our cell phones. So obviously we think microelectronics and semiconductors are important. Of course, they go way beyond that. And the demand is only going to grow as people always want more and more information processing. So we need not only the right materials, but the materials that can be reused, recycled, and friendly to the environment in microelectronics processing. This is a very active area. And finally, you may not think of it, but materials are important for pharmaceuticals. You tend to think of molecules, but I want to highlight an example of glass in the center there that was needed to make containers for pharmaceuticals that are chemically durable, mechanically durable, don't dissolve any glass into the medicine or the pharmaceutical. And so that's a very high-tech industry also. Of course, in defense, we need advanced materials, obviously, for vehicles, helicopters, aircraft. There's enormous stress on materials when aircraft operate. But again, people are looking into better uniforms for soldiers, as we indicate in the center here, which protect the soldier, which provide capabilities for the soldier in dangerous environments.
And I know, obviously, with high-tech technology and materials and applications, that's really, really, really a big component of this. But when I think about technology, though, I think of, obviously fighter planes and, like you mentioned, some telescopes and things like that. But you're also talking about materials in soldiers' uniforms?
Yes, absolutely. In fact, CCMR has a number of faculty members who are fiber scientists. We have a very strong department of fiber science at Cornell. You can imagine, we'll hear a little bit more about this, but there's an active area of development of uniforms for soldiers to prevent them from dangerous things like electrical arcs, also from chemical exposure. So this is antibacterial materials are needed for frontline combat. And of course, we need the best possible materials for cables, for ships and for helicopters and vehicles. As you'll see in the next clip, fiber scientists may have very basic physics and chemistry training. And this is a huge advantage because they understand fibers from the atoms and molecules up. And as you can imagine, that's very helpful for development of new fibers, basically developing fibers from first principles. In particular, Professor Hinestroza integrates materials called metal organic frameworks, or we say MOFs because that's too many syllables. He integrates those into fibers. A MOF you can think of like a crystal. A crystal has a periodic structure. It has a unit that repeats and repeats in all three dimensions. But a MOF has a hole in the middle of the unit cell. We call it the unit cell. So think of it a little bit like this. You have a coffee filter at home. The coffee filter has holes that are about a micron in diameter that lets water through but stops the coffee grounds.
Of course.
A MOF is a filter, but the holes are the size of a molecule. They're about a nanometer. Okay. So these can be used to trap, they can actually be used for filters for molecules, and they can be used even to trap atoms in a gas, for example.
Oh, wow.
So that's an example of the most advanced fiber science that's being done.
That's amazing. It's so amazing to think that, obviously with Professor Hinostroza's work, being able to break those fibers down to the atomic level, it's fascinating. And actually, speaking of Professor Hinostroza, let's hear from Juan. Let's bring him back on.
Why it's important to continuously improve and innovate in critical industries is because these industries are evolving really fast. Power generation, defense, air pollution. It requires also a protection of the workers. We are dealing with the life of the workers in this particular condition. So we have to innovate how to protect workers against different challenges of these industries. Optics was an amazing challenge for us because we were tasked with finding a solution to a problem that the industry didn't even know they have. So we have an issue of high voltage electric discharge. We call them arc flash. And that kills a lot of people, a lot of workers in this environment. And this company had a very unique challenge, how to protect the workers in this particular industry and how to capture the gases, the toxic gases that are generated in an arc flash event. So we work with the students, we work with the industry, we work with the company, that is a local New York company. We work with the CCMR through the Jumpstart project to find a solution based on metal organic frameworks that were placed on textiles, not only to protect against the high energy discharge, but also to capture the toxic gases that were a result of that. The same way that high voltage can kill people, very tiny electrical charges can actually save people. And that's what we use in masks that are respirators or masks against pollution. All of us remember COVID-19, so we have to wear an N95. This particular mask have electrical charges. In my lab, we pioneer ways to measure the location and the magnitude of these charges in a single fiber. And this is very important because we have issues of pollution, we have issues of illness, we have issues of disease. So having a massive protection is very important. A metal organic framework is a fascinating molecule. It's composed both of a metal and an organic compound. So we put them together and they have these very unique cavities that you can use them to capture different compounds. We use them a lot in protective clothing for defense, for industrial applications, because we can capture toxic compounds, and inside this cavity, we can actually decompose them into less toxic environments. So in our lab, we have been working for 12 years with these molecules. They are very unique, and then we can tailor them to capture very specific gases. All these three projects, even though they are in different industries, like power generation, like national defense, or air pollution control, they have something in common, which is to protect the persons, to protect the humans. And that is a very difficult challenge because every time you involve a human, you have to deal with psychology. Our sizes are different. Our faces are different. So matching these unique challenges is very, very complicated. But luckily in Cornell, we have all the tools to solve these problems. We have specialists in human design, like in our department. We have a specialist in material sciences. And the CCMR put them together to find the unique solutions to these challenges.
It's so interesting to listen to Juan and just listen to kind of all the different things that go in it, just like, even different sizes of people. It's so fascinating. But one thing I'm sure coming up with new materials obviously isn't easy as just, developing the idea and then obviously making the product. What other considerations or even challenges are there in advanced material designs when we're, kind of at the very beginning stages?
Well, whether it's the beginning or with an existing product, one of the things we've been helping companies with recently are so-called supply chain issues. Okay. These are when any product that's made is the result of a complicated, interconnected network of materials, suppliers, components that come together into a product at the end. And anything that disrupts those flows can be a problem. And as a result of the pandemic, supply chain vulnerabilities or supply chain issues are common. That's a common expression to all of us now, like it or not. So let me give a few ways this can happen. In general, they can be economic, environmental, political, or ethical. And I'll give a couple of examples, although not in this order. If we start out with ethical threats, just one example, what if you find out your supplier does not have adequate controls to prevent forced labor. Then maybe you can't work with that supplier and you have a problem delivering your product. You can see some other examples here. Economic threats, these are probably the easiest to understand. Inflation, prices go up, or even more broadly, let's say a component goes up in price. Let's say a component doubles in the machine that you're making. What do? There may not be room. The market may not be able to absorb the cost of passing that on to the consumer. So you have a problem. You have to go look for a new component. There are environmental supply chain threats. For example, we're familiar with storms, wildfires, other environmental factors that can impact production, or the supply of natural materials, or destroy natural materials or raw materials. And then, of course, unfortunately, in the news recently, we hear of recent examples of political threats to the supply chain. For example, the presence of a war can reroute cargo ships is just an example. So we've heard a lot about those.
Of course. And can you give us some insight into how shortages impact the production and even the innovation of advanced materials?
So I'll say this, it's really hard to appreciate supply chain issues if it's not your job. Okay. I know I didn't appreciate them till I was part of a company. And you realize, we actually can't deliver things suddenly. And people will say, find another supplier. But you may look for another supplier. The material they produce may not meet your spec. They may not be reliable. They may not be able to meet your demands, the amount of material you need. So there can be real issues. And of course, supply chains are vulnerable when materials or components are precious. So kind of by definition, there aren't going to be a lot of suppliers for them. Okay? So an alternative to looking for another supplier is to look into innovation of the components or the materials to come up with components or materials on your own. And we're going to give an example. CCMR recently worked with a company who was no longer able to source a specialty component that was really the key of their product. So you're going to hear about that now with Professor Baker.
Perfect. And actually with that, let's hear from Professor Chef Baker, who's over there with Frank at the College of Engineering.
I'm Chef Baker. I'm a professor in the Material Science and Engineering Department here at Cornell. My group looks at mechanical properties of materials, and particularly we're very interested in thin metal films and their mechanical behavior, which is different from bulk materials. So we have a big research program doing that. Calmetrics makes X-ray fluorescence calibration standards. X-ray fluorescence is a method that lots of companies use and lots of people use to measure materials. Basically, if you have a material, you shine X-rays on it. The X-rays cause the material to fluoresce. That means it emits other X-rays, and you measure the X-rays that are fluoresced, and you can find out what elements are in the material, and you can also use it to determine how thick a layer is. So companies that make thin coatings like to use these machines to measure the coating thicknesses. Calmetrics had been making chrome calibration standards. These are very thin layers of chromium, and these layers were the trick is to make these layers very, very thin, and the way they had been, that their foils had been supplied was they were made by rolling. So this is a mechanical compression process. You can imagine you had a couple of rollers that are rolling like this, and you've got a chrome sheet that you feed in one side, and the rollers press it down and squeeze it down to make it very thin. And so this rolling process is a standard metallurgical process that's used for lots of different kinds of metals. And the problem is that chromium in particular is very difficult to mechanically deform because it's very hard and it's very brittle. And at some point their supplier quit supplying them with this material because it was difficult, and other people could not figure out how to make the rolling work. And so they came to us, and we proposed to try to make an alternate version where we would make these thin layers by sputter deposition. So this is a process that we use in my research group. And sputtering works in this way. You start with a block of solid chrome. You put a gas in here, and you turn it into a plasma. You basically strip off the electrons, makes the gas atoms charged, and then you can use the charged atoms, accelerate them into the chrome the chrome target and then knocks the chrome atoms out, and they drift back through the plasma and land on the substrate where you're trying to grow this film. This is a complicated process. It has lots of different parameters that you can control, but you can make a coating, a chrome coating, and you can control the properties of that chrome coating over quite a range. The difficulty with this sputter deposition process, it's very difficult to make a layer that's thick enough for their calibration standards. The thicker you make it, these films tend to have very high stresses, very high mechanical stresses, and so they tend to crack and peel off and break. And so this was not a common way for anybody to make thick chrome layers. So I had a very good PhD student, Nate Rogers, who worked on this. We used an AJA deposition system that's at the Cornell nanofabrication facility. You're looking at a picture of that one here. That's what that machine looks like. And we used that to work out the parameters. And what we did was we figured out a way, a set of parameters that we could use during sputter deposition to make thick films that were fairly stress-free. But then the problem with that is that when you make these thick layers, thick stress-free layers, the surfaces are microscopically rough. And so they appear, when you look at them, they appear dark, they appear gray or even black. So they're not shiny like you expect chrome to be. It's still only chrome, but that rough surface makes it look dark. And so Calmetrics was afraid, and I think they were right, that customers would look at that and think, well, this can't be a good chrome calibration standard because it doesn't look shiny like chrome should look. You're used to seeing shiny chrome on motorcycle exhaust pipes and other things that you put chrome plating on. And so the trick was, what Nate figured out to do was, we made a thick chrome layer that was dark and ugly, and then he used a different set of process parameters to put a thin layer on the top of that was nice and shiny. So it was still all chrome, still met their requirements. And then once we had those process parameters worked out, then we could transfer that to a different machine at CCMR, where they could make many of these things at different thicknesses that could provide Calmetrics with some raw material they could use to make their calibration standards. And I think those calibration standards lasted them a couple of years while they were working out a new source for their supply chain. And so that was one way that we could take our fundamental knowledge of material science and turn it into something that could be useful for a small New York company that wouldn't have the resources to do this otherwise.
That was Professor Shefbaker. And along those lines, Frank, it's something that, I don't think any of us really think about as far as, where the individual components come for some of our products. But regardless of the reason for a shortage, it sounds like CCMR can help companies find an alternative and sometimes even maybe a better material for their product. Can you share just an example of innovations in use-inspired design and development that have led to more sustainable supply chains for maybe some advanced materials?
Sure. So if we think back to the supply chain threats that I mentioned, we can actually think of sustainability as a new one, if you'd like to. Of course, components and products that don't take sustainability into consideration are not going to be competitive in a future economy. Sustainability is just too important to people and to the world now. So what does this mean? People need to look into reducing energy in the production of their product, reusability of materials or materials that easily biodegrade, reduction of harsh chemicals that can be damaging to the environment, expensive to produce, etc. Those are all examples of that. One example that we saw already is the coffee cups, which are made from bio-waste, which is an excellent circular manufacturing process if it succeeds. Another example, CCMR is currently working with a company called Wearwool, which is based in New York City, who's working with Professor Larissa Shepard on an interesting new approach to making colored fabrics without using dyes. And the reason to do this is because dyes can be particularly toxic and hazardous materials.
That's so interesting to be able to get that color. And with that, let's hear from Professor Larissa Shepard, who's an assistant professor over at Human Ecology, and Julian Lee, who's the co-founder and actually CEO of Wearwool.
Hi, my name is Larissa Shepard. I'm an assistant professor in human-centered design at Cornell University, specializing in fiber science. At the Responsive Apparel Design Lab, or RAD Lab, our current interests are in making the world better off by developing optically responsive fibers and fabrics, which we have termed OFFs. We are able to create these fibers and textiles in a variety of ways here in human-centered design, but in the RAD Lab, we always start at the nanoscale level and build up from there. For example, We have created chiroptical strain sensors from cadmium sulfide quantum dot fibers that show not only changes in chirality, but also visual changes under cross-polarized light. With more research and by creating camera systems which could visualize these changes in field, one important and potential future application is for high-resolution visual inspection of stress and strain in structures, such as those that are highly deformable, like airplane wings. Our impact doesn't end here. We are also looking at big world problems, such as food production. We are developing methods to increase crop yield by creating fibers and textiles that can convert sunlight into more desirable wavelengths of light for photosynthesis. In these projects and others, characterizing and analyzing fibers and fabrics for their properties is of the utmost importance when considering their efficacy and applicability in real-world scenarios. Cornell's Center for Material Research provides access to many of the instruments that make this research possible, and in short, is an indispensable asset to the labs around campus. The RAD Lab, through CCMR's Jumpstart program, had the opportunity to work with Wearwool, a company harnessing recombinant protein structure to create an array of fiber with intrinsic color and function without the use of petroleum-based polymers or dyes.
Hi everyone, I'm Julie Lee, co-founder and CEO of Wearwool. Our team is currently developing fibers with color and stretch built in at the DNA level of our materials.
We were able to characterize the mechanical strength of Wearwool's fibers and provide insights into how their fiber-forming processes were affecting the integrity of the fibers themselves. When we think about dyes in our textiles, they are using harsh chemicals that can often end up polluting waterways. By using alternate methods to create color, this provides a viable option for colored textiles without the use of harmful dye-related chemicals.
For new biomaterials, it's extremely important that we meet or exceed incumbent material properties to be viable for implementation within the textile industry. And at Wearwool, we are developing a novel textile fiber that eliminates the toxic chemical solvents, plastics, and dyestuffs traditionally used for the clothes we wear. This is an iterative process that requires a lot of feedback on our materials so that we understand how different processing parameters that we are developing ultimately affect our end products.
It was exciting to be part of this project as it fits in within our scope of the RAD Lab, which is making the world better off by finding alternate avenues to synthetic dyes that are able to generate color in fibers and textiles. Who knows, maybe your next textile might have proteins involved.
Cool. Thank you so much, Larissa, and thank you so much, Julie and Lee, for your contributions. And just very, very quickly, audience, we do have some time at the very, very end to answer some of your questions. So please feel free to open up that audience chat, submit your questions. And like I mentioned, we have reserved some time at the end where we'll get to some of your questions. And I know a few people have started to ask questions, so please continue to submit those. But with that, when I think about growing materials from fabrics, and Larissa mentioned a little bit fabrics from protein, and maybe it's just me, I imagine wool from sheep or, obviously cotton from plants. I definitely don't think of growing our own color or stretchness. That's interesting.
Well, so that's an example of how knowing the science from the atoms and molecules up can enable you to design for certain properties. And in the end, a dye is actually just a molecule that we understand. And this is a case where we can come up with different molecules and different structure of the fiber that will allow us to have the color without the toxic and hazardous properties of the dye.
That's so interesting. And how are new or maybe novel advanced materials being developed to mitigate supply chain risks and other considerations moving forward?
Well, we've heard the example from Wearwool. We heard the example from Return Bio using the coffee cups. And I'll mention one more, which is a big area of research now. And that's so-called green materials for photovoltaics. There's a push, of course, to get more of our energy from photovoltaics.
Of course.
Among the most exciting future materials are so-called lead halide perovskites. These were discovered maybe 6 or 7 years ago, maybe 10, and almost immediately became about the most efficient solar cell materials.
Oh, wow.
But they have the advantage over existing materials that they can be solution processed. That means made in liquid form and basically painted on to materials. Oh, wow. I'm exaggerating a little, but they have huge advantages in the production. Everything sounds good about them except lead. You heard the first component is lead. And lead has already been forbidden as a solar cell material by many countries. So people are working very hard now to find substitute halide perovskites that don't depend on lead that can be used to make solution process solar cells. Wow. So that's another example where there's a sustainability issue, an environmental issue, And this of course, has very high potential impact in the world, and a lot of efforts being devoted to it now.
That's so interesting. And we talked about where advanced materials come from, the differences between natural and synthetic, what use-inspired design is, supply chain threats that influence the development and production of materials, and sustainability and material development. So now we are ready to make our, widget. Can you discuss the role that the manufacturing process plays during the material design of a product?
So there's often a big step between the science that researchers do in the lab to first demonstrate a material property and being able to manufacture it at scale.
Okay.
So scientists first make something that might have a gram of sample or some tiny amount like that, just enough to be able to characterize it, its chemical properties, its physical properties, etc. Then they might scale up to a milliliter of material. Okay. Once you start to get to a liter or to production volumes,
it's a big difference.
It's a big difference. The machines that produce the huge volumes in manufacturing are going to have thermal effects on the process. They're going to have handling effects. There are a lot of things that can happen. And it's very common for companies to struggle in scaling a manufacturing process up to something that's realistic from what's been done in a research lab.
Of course.
So that's a general problem. It's especially true for polymers or plastics. And we'll give an example. A couple of years ago, we worked with a Rochester-based surgeon on a medical device that she invented to help with surgeries. This is a device that absorbs infrared light, and I'll explain it. Infrared light can be transmitted through tissue, which means if we could see infrared, we'd be able to look better through tissue.
Okay.
And a doctor has trouble looking through tissue during surgery.
Of course.
So this surgeon, designed a device that absorbs infrared light that's used to illuminate a body part during surgery and converts it to green light. And the value of that is, of course, humans can see the green. So this is a way to do infrared imaging, but have it visible to humans. I don't think I explained that as smoothly as possible, but I hope you get the best idea. I hope you get the main idea. The bottom line is this allows surgeons to effectively see the structure in thick layers of tissue. She formed a company, she co-founded a company, and they made prototype devices, and they worked very well. Then they went to manufacture them at scale and by injection molding, and found real problems, and the devices didn't work anymore. So at that point, she came to the CCMR for advice.
And that's, like you mentioned, the scaling up from the, small milliliter to the liter very much. And actually, speaking of that, let's hear from actually that surgeon, Dr. Paula Doyle.
Hello, my name is Paula Doyle, and I am a reconstructive pelvic surgeon from the University of Rochester. In 2018, Endiglow was born, name of the company. Currently, we have a lead device. This is what it looks like. It is called the Green Egg. It's made by Endiglow, and it's this top portion that fluoresces under near-infrared imaging. When we look at this with the naked eye, it looks white. But if you were to be operating and turned on near-infrared camera with the correct filters, it would look like a bright, glowing green. So when we talk about polymer manufacturing, this is not just your everyday type of plastic. This is really a special type of plastic that needed additional science and needed to understand where the physics of polymer materials came together, and also where the chemistry of the dye comes together as well. And that's really where Cornell's expertise was invaluable. And for this reason, we reached out to Cornell and the Cornell Center for Materials Research, and they really helped us take the small batch idea and commercialize it into large batches. And this is not as easy as you might think, because this fluorophore, what actually makes it fluoresce, is very heat sensitive. And our polymer is going to go under multiple rounds of heat exposure. For example, when we first make the polymer, everything needs to be melted down. That's one round. And then it needs to be melted down from a master batch into a diluted batch. That's a second heat exposure. Then, when we injection mold a surgical device, that's a third heat exposure. And then when it is sterilized for the operating room, that is a fourth heat exposure. And so CCMR really helped us take a lab idea and small batches of this polymer and be able to bring it up to commercial levels. And my goal was to make medical devices that fluoresce under near infrared. The reason why this is important is for a few things. So one is near infrared is pretty ubiquitous in the operating room. All of the surgical systems that we operate with have near infrared capability. And the reason why they have near infrared capability is because seeing in this wavelength allows the surgeon to see through tissue. It allows the surgeon to see through blood to about a centimeter. And you can imagine if you were operating in a bloody surgical field that it would be advantageous to see through the blood to the region of interest. So right now, Endiglo is selling commercially. We are in operating rooms. Surgeons are using this on a regular basis. And the benefit is the transillumination or the fluorescence of our material. So the device that I gave you, or I showed you this one, this egg manipulator is what it's called, goes into either the rectum or the vagina. And the transillumination or backlighting allows the surgeon to see relative tissue depth, can see scar tissue, can see pathology that is not sitting on the top surface. And I think we all can agree that if a surgeon can see better, they're more likely to do a good job than if they can't see very well. For example, endometriosis. Endometriosis is a disease, mainly in women, that seeds all over the pelvis and other regions. And it doesn't just sit on top of the uterus or on top of the bowel. It can be found deep within as well. So it's difficult for the surgeon to scan an area and look and be able to identify all of the endometriosis. They can identify the surface endometriosis, but anything deeper would require additional investigation and enhanced visualization like we can get with the Endiglo Green Egg device.
Well, thank you so much, Dr. Doyle. It's really, really fascinating to hear that success story. It's just mind-blowing, some of the things she can do with her egg there. And I just very quickly want to touch on the partnership between you and the entire CCMR team and Fuse Hub. So for the New York-based companies in our audience, what is this new program?
If you need to change materials in your manufacturing process, that can take a lot of work.
Of course.
You might have to just do new quality control on materials that come in. You might have to redesign your whole process. So it could be a big problem. CCMR is working with Fuse Hub on the Advanced Materials Manufacturing Readiness Accelerator, which is geared toward businesses exploring new materials in existing product designs and startups too. So this program has specific materials and industry experts to help your company maintain competitiveness if you need innovation in advanced materials. If you're a New York State company with working in advanced materials and you heard anything today that you think could be helpful, please reach out to CCMR or to Fuse Hub, and we would be happy to help.
Perfect. Thank you so much, Frank. And we, again, audience, will put that link in there in the audience chat for you as well, just for a little bit more information. So before we wrap, we just have a couple audience questions very, very briefly. So this first one is from Kim. So Kim asks, manufacturing organizations produced waste within their facilities and waste that the customer eventually disposes. Do you see the future of responsible manufacturing developing sectors within organizations that take on the recycling of materials to reintroduce them as advanced materials? I know there's a lot there.
Hi, Kim. Thanks for the question. A little bit beyond my expertise. But let me say the answer is yes, and hopefully you've seen a bit of an example of that today, for example, with Return Bio. For a better answer than that, though, I'd refer you to the Industrial Outreach Program of the CCMR. Please contact us and we'll be able to give you more information.
Perfect. Thank you so much, Kim. And just very, very briefly, Victoria also checks in and she asked, could you send us the complete name of the professor working on fibers? And I believe it was Juan Hinestroza. And then she asked, what is usually the type of process you use for making the fibers, or what Juan was talking about?
Okay,
earlier?
so I would have to defer that question to Professor Hinestroza. He's the expert in it, and I can't really speak to that, but I'm sure he would appreciate hearing from you, and we want to encourage you to contact Professor Hinestroza directly.
Perfect. Frank, thank you so much for joining us today. And audience, again, if you're part of a New York-based company looking to advance innovation of a product, we'll share the link to the initiative one more time. Again, audience, you can find that in your viewer chat there. Also, if you're watching the recording, those links can also be found at the bottom of the registration page as well. So anybody rewatching this event, again, at the bottom of the registration page. And just very, very quickly, let us know how we did. We appreciate your feedback. We do look at your responses, so please let us know how we did, ways we can improve. Again, Professor Weiss, Frank, thank you so much for joining us. We really appreciate it. It's great to have you back on. Audience, thank you so much for staying with us and for your responses, and we'll see you at the next keynote. Have a great afternoon.